Hello, welcome back. This is the second session wherein we cover how to make a kernel-wide configuration change for the anti-Linux RT kernel and boot it on any number of anti-Linux RT based targets. What this is going to be doing is setting up the stage for some work that we're going to do in future demonstrations. Again, this is the second video. The very first we cover getting the tools, getting things configured, and building just a bone stock kernel configuration and booting it on our target. Just kind of talking through what pieces are needed and how to actually build a base kernel. So this session we're going to cover the Kbuild system, what it does, what it provides, and make a system-wide kernel configuration change. So with that, let's go ahead and get started. I've went ahead and already set the environment variables that are going to be required. So if I just go ahead and check for the cross compile, that's already been set, and the arch has also been set. Again, these are no different than the instructions as laid out in the NI GitHub instructions for building kernel that were referenced the first video. So let's see here. Let us go ahead and get started with the Kbuild system. What you'll note is if you just look through the kernel source and you look for just make files, what you'll note is that pretty much every single directory has a make file that is associated with it. And what's interesting about the make files throughout the tree, they're a little bit unusual in that very few of them actually define a traditional make file type rule. They're just setting variables. It's actually the top level make file and some of the make files under the scripts directory that really consume the variables that are set in these sub make files and actually make things happen with regards to building objects and linking them into the kernel, or making essentially kernel modules or .ko files. So if we just pick one of the random make files to look at, we can see what it is that I'm talking about here. So let's look at, I don't know, drivers, USB core make file. Sure, why not? Okay, so what you'll see here is what I said. There are no rules, no GNU make type rules defined here. They're just some variables that are set. And you'll note this one is really the one that makes things happen. There's this obj object hyphen and then the config USB variable, and this can either be a Y if it is configured to be built into the kernel, or an M if it is configured to be built as a module. What this also shows is, okay, it defines if you've enabled USB, config USB, either to be built into the kernel or be built as a module. And I'm jumping a little bit ahead, but we'll get there in just a little bit. It depends on this USB core.o file, and you see USB core dash and then some additional configuration options, either PCI or ACPI. What these mean are, if you have either PCI configured, then what this will do is, for the USB core.o file, also depend and build this HCD PCI.o file. There are built-in rules for this particular type of a requirement, and what it will do is just find the HCD-PCI.c file and use that to generate this .o file. It's fairly common amongst makefile, especially more complicated makefile systems. and also just GNU Make itself has implicit rules for this sort of thing. There are some that are just always defined. So USB core, yes. So these will always be enabled. So these will always be put into the USB core.o file. USB core.o is just an amalgam of these if the associated configuration files are enabled, or the configuration options are enabled, and these are always glommed into this USB core.o. And again, just to wrap up, if config USB is set to yes or built into the kernel, this will get linked into the actual kernel image. If it is configured as a module, as a loadable module, then what this will do is it will result in a .ko, a USB core.ko, which can be manually loaded or unloaded. So let's take a look at where exactly these config options come from. So if we do the same sort of operation and we just look for the file name kconfig, and we actually give it an asterisk, what we can see is that there are also a bunch of different kconfig files all throughout the kernel source, pretty much in the same directories as the make files themselves. So if we go ahead and look at the accompanying kconfig file under the driver's USB core, we can see that we see these config and then the name. And essentially, if this is chosen, if this configuration option is chosen, it will define in the topmost kernel configuration file the all caps config underscore and then whatever the option is. And what you'll see is in this particular folder, in this particular one, it doesn't actually define the USB config. The USB config is actually going to be the previous, and what that's going to tell us is if it is enabled, then we would actually go into a subdirectory. Let's see here. So here's the config USB. Support for host side USB, just a short little description. Tri-state means that this particular option can be either disabled, enabled and built into the kernel, or enabled as a loadable module. It notes a dependency that this option won't even be an option if this particular configuration is enabled or not. And sometimes this is architecture specific and not something that's selectable by the user. And sometimes it is something that is absolutely an option that a user would enable in order to get access to this. And a good example would be, let's say that, this is a good example. USB Arch has HCD host controller. And what this means is that certain architectures will define this particular configuration. It is not something that is selectable by the user. It is either enabled or not enabled for a particular architecture or a certain machine in some certain cases where a machine defines a particular implementation of an architecture. Another good example would be, sometimes PCI is not always an option on some devices. It just isn't built in, and in other cases it is optional. You can either have it or not have it, and some it's actually built into the architecture, the processor itself, or the system on chip itself. Others that are selectable would be, for example, let's say some wireless functionality depends on certain cryptographic routines. That particular wireless operation would be dependent on those cryptographic routines being available in the kernel. So they either are turned on and built into the kernel, or it could be as a loadable module perhaps. So that gives you kind of a brief overview on these two different file types. And we'll go ahead and take a quick look at what that actually means for the user. If you use a built-in make target called menu config, what this is going to do is essentially gather up all of those kconfig files, the descriptions, things like that, and use the arch environment variable that we've already set as ARM to go ahead and pull together a list of all of the different configuration options that are available for us to go through. If there's no user input, no choice for the user to make, those will just be enabled or disabled silently, but any configuration options that actually allow for there to be either a Boolean or a tri-state type selection made to enable or disable, those will be collected up, and using the structure of the file system that the kernel source has, that will be used to go ahead and kind of create a hierarchy of configuration options. And instead of just trying to explain it, let's actually take a look at what that looks like. So you can see this provides us a pretty reasonable text-based kind of menu. Oh, let's not do this. Made a silly mistake here, so let's go ahead and clean and make proper. And I forgot to actually pull in the NADI, the National Instruments default configuration. So let's do that real quick. Sync def config. And let's try that again. What that actually did the first time when I made a mistake, what that did is actually use my laptop, the default configuration for my laptop, as a basis, which different architectures, different distributions, that's something to be very, very careful about, and I'll do that from time to time. So that's just something to keep in mind. If you have run a make mr proper, which will clear out the configuration file and just clean up some of the configuration things and kernel build artifacts that are not just .o artifacts, you will need to go ahead and reload the default configuration. So anyway, back to where I was. Fundamentally, what this has done is just to use the kconfig files to compile a hierarchical menu for setting different configuration options. And anytime that you see an asterisk, that means that it is built into the kernel, and the two little characters to either side of the asterisk give you an idea of what the operations are that are available for this. Fundamentally, this patch physical to virtual translations at runtime option, this is enabled and force enabled by some other option that we've chosen, so we can't disable this. Normally you would just hit N, and hitting N has no effect on that. If we wanted to see what's causing this, what we do is just hit the question mark key. This will pull up the more complete description that we saw in the kconfiguration file. This will tell us what the symbol actually is, the config _ arm patch, so on and so forth. We can see where it's defined. It's defined in this particular kconfig file under the ARM architecture subfolder. and we can see what it depends on and what it was selected by. This is what is causing us to build it in without choice. And basically it's this notion that there are a couple of choices, namely the, let's see here, a couple of choices that cause us to build this into the kernel. So let's go ahead and go into one of the subfolders, and I'm going to just go into the kernel hacking. This is, again, as I mentioned, setting up for a future demonstration. So we can see here there are a couple of, underneath the kernel hacking directory, which you can see in the upper left-hand corner here. There are a couple of other subfolders underneath here, and pretty much every time you go into one of these, it adds some additional information to let you know exactly where you are. And if you hit escape twice, that gets you back out. If you hit enter, that lets you go into a subdirectory, into a subfolder. So let's go ahead and go into compile time checks. And what I'm going to do is just hit Y or yes. As you can see, we have square braces here, which means it's a Boolean. It's either enabled or disabled. Angle braces will allow there to be either a yes built in, yes built as a module, or no, a tri-state. So let's go ahead and compile the kernel with debug information. And let's see here. We will go ahead and enable the kernel debugging subsystem. And you can see here, here's an angle brace option, which if I hit M, this will build it as a module instead of being built in. But for our purposes, I'm just going to build it into the kernel. And I'm also going to enable the KGDB, KDB functionality, which, if you are familiar with GDB debugging, especially GDB server and GDB, using the two in conjunction with an embedded system, the KGDB system is very similar to that. The kernel's KGDB taking the place of the GDB server in terms of providing up a kind of a minimal set of functionality that GDB can connect to remotely. In our case, it's over a serial cable. And the KDB it's actually an all-in-one or a self-contained but reduced debugging system, where the serial console essentially acts as a minimal set of operations that you can perform, so that you can at least get an idea of what is going on with your system. But the nicety is that with KGDB and KDB enabled, it's going to default to KDB, and you can essentially switch it back and forth between the self hosting or self-providing debugging facilities in KDB, and the little bit more powerful but requires some additional setup KGDB subsystem, so you can switch back and forth between the two. All right, so let's see here. I am going to back out and save the configuration. Every time that you save a configuration, it's going to go ahead and save the config in your .config file, but it will also save your old configuration in a .old file. And the differences here are going to be more than just KGDB and debug information. It's essentially some additional options that needed to be enabled or were set true by default as we were enabling things. So with that, what I'll go ahead and do is just go ahead and start a build. This is going to take a while, so I will pick back up when it is finished building. This is, again, using the same instructions that that are on the GitHub page, the NI Group's GitHub page, that describe how to use the kernel source to build a kernel. So I will see you in a few minutes. Alright, the kernel build has finished up, and what I'll go ahead and do is copy over the modules. I'm going to go ahead and skip reversioning the NI modules, since that's not really important to what it is that we're doing. If you are interested in that, it's covered in the first video. It's also in the instructions on GitHub. Let's go ahead and just copy over the kernel and modules. Okay. Copy the ITB over to our controller. Oops. There we go. And we'll go ahead and archive up modules. What you'll notice is copying over the modules this time takes a little bit more time, and that's because the kernel modules themselves actually have the debugging information present in the actual modules themselves, which help aid in debugging. Alright, so let's see here. Again, we're currently using the kernel that we had built last video. Let's go ahead and reboot. And I'm just going to go ahead and do a quick demonstration of some of the debugging stuff. We'll cover this in a little bit more pragmatic detail when we do an out-of-tree kernel module, which I've purposely put a bug in the actual kernel module itself. So we'll dive in a little bit deeper in the next video, but for the time being, I just want to show that first we have indeed booted our new kernel. If we go ahead and look at, there is a particular file called config.gz. It's a pseudo file. It doesn't actually exist on the file system, which contains all of the configuration information for this particular kernel that is booted. If we look for debug info, we see that debug information is built into this kernel. It's enabled for this kernel. And if we look at KGDB, we see that KGDB is enabled, Zero Console is set up, and the KDB subsystem is also enabled on this particular controller. So what we actually want to do now to enable KGDB, because right now it's not enabled, if we were to have an operation that would traditionally trigger KGDB, either a kernel oops or a panic or a KGDB breakpoint. You can insert breakpoints into your code. That's kind of like an assert type of deal, where it'll break into the debugger or really cause a kernel oops or debug break. Nothing would happen. Debugging is essentially not enabled right now. And what you would actually need to do this, and it's covered in great detail in the actual kernel documentation folder. If we look under documentation, let's see, I think it's debugging. I'm not sure. It's somewhere in under documentation, I'm sure. It covers exactly what needs to happen here. Actually, just real quick. Need to be to cursive list be under documentation, and yeah, there we go. So it's then documentation, GDB, kernel debugging. And yeah, this covers KGDB, and it tells you the KGDB over console. Oh, no, it doesn't. It's going to be in the other one. Let's see here. Actually, it's going to probably be under kernel parameters for console. It tells you allow kernel debugging, that's the wrong one, KDDB of console. This basically tells you all that you need to know in terms of enabling debugging over a console. The other document about GDB kernel debugging will tell you exactly how to enable it, I'm sure, yeah. This short tutorial about how to enable and use them, so on and so forth. I'm not going to go through it. It's in the kernel documentation, in the kernel source itself. I definitely recommend just giving that a read. But for the time being, let's go ahead and just enable debugging. And what you actually do is write to a pseudo file, a different pseudo file, the device I want to use for debugging, the TTY S0, first serial device, the baud rate that I want to use, same baud rate that I have right now, and I will send that to sys module KGDB over console, parameters KGDB over console. And what you'll see is as soon as I do that, there's a kernel debug message, or a kernel log message telling us that the I/O driver KGDB over console is registered, and that's also synonymous with essentially debugging is now enabled. We can actually trigger a debug break without actually inserting a KGDB breakpoint in kernel code by echoing the G character to yet another pseudo file. And all of this is covered in the documentation that I pointed out before. But this proc sys request trigger is useful if you can't send break commands, which I can do over console. I'm just showing this as another option. Really it kind of depends on what what terminal program you're using of how to send a break command. But it would basically be break G, and you basically send it to proc sys request trigger, or you can emulate the same behavior as sending a break followed by a character by just sending just that character and writing that to the sys request trigger. What we'll see is this is going to go ahead and change our prompt to the KDB prompt, and it tells us that, hey, we're now debugging. It shows us what the current process PID and what its task structure, where it's located. Let's see here, and if we just do a question mark or H, what that'll do is just give us a breakdown of all of the different commands that are available to us. And what you'll note is there is a command KGDB, I'm sorry, and that says that it will cause KDB to enter KGDB mode. So if we do that, well, first let's just do a backtrace just because. So we see just some symbol information and offsets into the those symbols, which is, you know, whatever address is after that. And you can use a tool, address to line, ADDR2 line, to go ahead and convert those offsets into actual line numbers. Or what we can do, and what I'll go ahead and do, is just switch that over to KGDB mode. It will thoughtfully tell us, go ahead and attach debugger or use these one of these two sequences of characters to go ahead and get back into KDB mode. And real quick, I'm going to go ahead and do one of the sequences, $3 $3, and you can see it brought us back to the KDB prompt. But I'm going to go ahead and just connect over KGDB using GDB. Since only one program can be used in the console at any given time, that serial port, I am exiting out of my terminal program. Let me go ahead and get to the same directory as the kernel source. I have built my own version of GDB just for ARM support. Let's see here. It's supports any and all targets that GDB supports, Linux or otherwise, which of course also means that I need to specify let's see here, new target to 32 little ARM. Basically, if I don't set the GNU target, it doesn't know exactly how to read the symbols from the VM Linux, the VM Linux file, which is the uncompressed kernel image itself. Then what we do is we go ahead and set the serial baud rate to match what the kernel has been told to use the serial console at the baud rate at for KGDB debugging. And then what we do is we essentially tell it that we want to target a remote system and we want to communicate to it through the dev TTY USB 0 serial port on my laptop. So again, TTY USB 0 is the serial port on my laptop. That's what you specify through GDB on the host. When setting up KGDB on the target, you specify what serial port to use on the target, which is dev TTY S0 on all NI targets that I'm aware of right now. If that changes, you would need to basically take a look at what the serial console is set up as when you turn on console out. It would be in the kernel boot parameters, which are available through the proc command line sudo file. There are also numerous other places where you can find out what serial port is being used. So now back to what it is that I would like to show you. So I'm telling it to go ahead and use dev tty USB 0 at 115 200 baud, and if we do a backtrace here, we see quite a bit more information. So we see the very topmost portion of the stack is in this architecture KGDB breakpoint in the ARM. Arch ARM include ASM outer cache file, and also gives us the line offset. If you are familiar with GDB, pretty much everything that you would expect to work cover is basically the same type of deal here. L to list where exactly it is that we're at 142, and you can switch frames. Let's go to just, I don't know, frame 8, sure, why not? What we can see is, unfortunately, quite a bit of stuff is optimized out, which that is something that you can work around through either going to a different portion of the stack or changing the kernel code to enforce something is not optimized out. There are a couple of options you can have there. Yeah, that, and same type of deal. If we just go ahead and right now, the target is actually broken in through KGDB. It will not respond to pings. So I mean, it's out for the count. It's down for the count, so to speak. We can set a breakpoint at pretty much any kernel object source that we wanted to, which we'll cover that in the next video. But what I'm going to go ahead and do is just continue execution. We're still connected to the target. What you're going to see now is that I can indeed ping the controller. And what I'm going to go ahead and do is SSH in. And what I'll go ahead and do is break in yet again. This time, actually, let's try. Let's just echo G. Thought that I'd remembered how to send break commands in my serial console, but I don't. It seems like I don't recall how to do that. So I'll just use this. And you can see as soon as I do that, it doesn't actually finish, like it doesn't bring up another prompt line, which is to say my SSH connection is dead. I mean, it will, the connection has not been closed. The kernel has just stopped executing that code. It's not updating anymore. And you can see it's pretty much the same as when I had essentially attached the first time. So this kind of just gives you a brief overview on how to make a kernel-wide configuration change. This would be this sort of system that you would use if you wanted to go ahead and enable a particular driver. Instead of going in and enabling debugging for the entire kernel, what you would do is just go into the particular area that describes the driver that you care about, whether it's some testing USB wireless device which is not mated into the normal wireless driver area of the kernel, or a particular USB serial adapter, or whatever, some unusual file system type or anything like that. This is where you would enable drivers, or a fundamental change in how the kernel behaves, or what sorts of options are available to it, either driver, file system, system-wide types of settings or policies, things like that. The kernel documentation is a really good resource if you wanted to find out more about that sort of thing. And of course, just searching online, just searching Linux kernel, and then whatever piece of hardware you have, or whatever piece of functionality you want to enable. Network bonding for redundancy or performance, or security options, things like that. Quite literally, there are far too many things to enumerate all of them. So I definitely recommend you just take a poke around. Remember the question mark key will give you additional information in the kernel configuration menu, that menu config screen. There are some different options if you wanted to use them. I just prefer menu config. It's low resources, it's easy to set up, and I'm just more familiar with it. But there are other graphical options, so I definitely just recommend you just try it out. If you have any questions, or if you have any concerns, make sure to just go ahead and post them as comments. And next time, as I mentioned, we'll go ahead and take a look at a little bit more in-depth kernel debugging, and specifically we're going to be looking at an out-of-tree kernel module, how to build it, and this particular one will have an issue that we need to debug. So until then, thanks for watching.